If AI networks are hitting their copper limits, what changes when we put light into the PIC? And how do we keep that light perfectly aligned? Hi, I'm Arturo Santiago, and joining me today, we have Ryan Vallance, Justin Bressi, Chris Heisler. Did I pronounce your name Heisler?
Yes, Heisler.
Heisler, I'm sorry.
No problem.
Yes. So we have really smart people today. And Ryan, if you want to just let everyone know who you are.
Okay. So I'm Ryan Vallance. I'm from Senko, and I'm the Vice President of the Emerging Technologies Group. So our group is responsible for kind of surveying the emerging technologies and making sure that we've got the right ones in the portfolio for the next generation of optical communications.
My name is Justin Bressi. I'm a business development manager with Aerotech with a focus on semiconductor and photonics technologies. Aerotech is a precision motion control supplier and has done business in these industries for decades. And so I've been working with Chris and Ryan here on solving the next generation of challenges for data center interconnects.
Hi, Chris Heisler with Santec Corporation. I'm CEO of Santec California Corporation. So our division kind of leads the light source development, the optical power meter development. And right now we're really focusing on CPO applications and PIC alignment.
Okay. So it's no pressure on me. I'm here with three alignment wizards and me not trying to lose 0.1 dB. So
hopefully we can find it by the end of the show.
So let me ask you this. For the viewers that don't know what silicon photonics is, who would want to answer what it is and how we got from copper fiber to silicon photonics?
Well, silicon photonics is it's a way for modulating light, right? Turning light into ones and zeros and being able to convey that data in a stream of ones and zeros across optical fibers in the data center or in the high performance computers. So silicon photonics fortunately gives us a way to integrate that with larger chips like switches and eventually CPUs and GPUs. So that data stream of those zeros and ones are now going to become principally transferred on optical fiber and as light rather than on copper.
Okay, nice.
Also,
nice.
I mean, silicon photonics, typically fiber optic communication was done just over fiber. And silicon photonics allows us to miniaturize a lot of these components so that we can fit them in smaller form factors.
Okay. So all three of you co-wrote a paper, a technical article on active alignment, which is one of the projects that we're working on at the moment. So why active alignment for CPO? So what's the one reason CPO makes active alignment harder than most people think?
So active alignment is kind of a key operation in the production of these silicon photonic devices or co-packaged optics. It is responsible for actually getting the very best performance out of the optical connector, right? So you do that by perfectly aligning that fiber optic connector with the chip. And what's maybe not recognized is that it's used many, many times in that production and packaging process. And so any improvement that can be done to that active alignment process is going to reduce the cost of production.
Okay. So, Justin, on your end, why do you think active alignment is harder than what most people think?
So for co-packaged optics technologies and the emerging silicon photonics technologies that are needed for next generation data center interconnects, the devices are first very, very small. They have high channel counts. And so there'll be a number of different signals that need to be aligned all simultaneously. If you look back in industry a decade plus ago, most of what was going on in fiber optics was single channel alignment. And these emerging technologies require many channels to be aligned, and therefore are also sensitive to more degrees of freedom. So when you're trying to align, if my fingers are optical channels, you try to align all these different channels in 6 degrees of freedom. So X, Y, and Z, and then TX, TY, and TZ, your 3 rotary axes. And so that presents a really challenging motion problem, which is kind of where Aerotech comes in, and partnered with Senko and Santec here to come up with a system to address those challenges. So the traditional approaches for active alignment really were optimized for those processes from the mid 2000s. Single channel alignment routines, algorithms that were written for simpler alignments, but co-packaged optics demands better alignment quality and faster times because of the scale of production that's needed for these devices. And so we've worked together to develop a solution for addressing that industry challenge.
Okay. And Chris, same for you. Like, why do you think it's harder than most people think?
Well, I think, when you have multiple channels that you're aligning, you typically need, you always need at least a nice stabilized light source, nice and quiet, so that the optical signal is stable, and the analog signals that you're analyzing out of this power meter is also rather quiet and stable. What makes it more challenging, though, when you have multiple channels is you have, maybe 10 channels that you need to monitor at one time. So a lot of times what a customer would be doing is aligning 2 channels at a time. What we want to be able to do is give them the ability to monitor multiple channels in real time. So that's what we've done, is we've kind of built our banks of power meters to have analog outputs, so that you can kind of gang the power meter channels to give you those signals, the real-time signals that integrate with the motion control systems.
Okay. So Justin, degrees of freedom. Degrees of freedom, me not knowing.
Yeah.
But when I heard that term, it's like, I don't know, I thought it was funny. And for whatever reason, every single time I hear freedom, I always think about Mel Gibson. You can, But what forced the move from planar optimization to 6 degrees of freedom? And what changed in the motion architecture?
So for single channel alignments, they're often only sensitive if you're trying to align 2 fibers, to maybe 2 degrees of freedom, searching in like an XY space, for example. But as you have higher channel count devices, the misalignments in your angular positions also start to matter a lot, because if you're lined up in X and Y, but you're misaligned in your this rotation, then all the channels aren't going to be aligned. You won't get signal across the device. Additionally, some of the emerging technologies, including some of the stuff that Senko has developed, really cutting edge connector technologies, are highly sensitive to those angular misalignments, even in very subtle adjustments. And so basically, you need to be able to precisely align in all 6 degrees of freedom in order to manufacture a high quality part. And so again, just to reiterate, 6 degrees of freedom is 3 linear, it's X, Y, and Z, and then 3 rotational axes. So the rotation about each of those linear axes. So it's a roll, pitch, and yaw, basically. And so that's your 6 degrees of freedom. And our algorithm that we've written together, enabled by the PIC-Align architecture, takes advantage of the multi-channel communication that Chris was just discussing, uses all of that data to inform our high degree of freedom searching, and performs that alignment of those devices using that information very, very rapidly in that 6 DOF space.
Okay, and so I want to ask you a question that when you were mentioning the alignment, 3 axis, when you're aligning them, when I think about an MPO, all the A12, 24 fiber, 36, whatever the empty ferrule has, is that a problem at the moment that could be fixed by the 6 degrees of freedom? Because if you're talking about alignment, I mean, obviously all the fibers are going to align into when you're connecting when you're plugging in the connector, right? What about the Z then? So at that point,
the MPO connector is kind of an interesting comparison, right? So if you think about the way an MPO is constructed, all of those fibers are in a plane. That plane has been polished, and there are guide pins that are aligning one connector half to the second connector half.
Mm-hmm.
So those guide pins are actually constraining some of those 6 degrees of freedom, right? They tend to constrain a rotational degree of freedom and then also a tip and a tilt degree of freedom. So in some sense, they're taking care of the alignment of those 3 rotational degrees of freedom. And then when you slide the pins into the 2 holes, right, now all of those fibers in the line are constrained in all 6 degrees of freedom because the pins have restricted those rotations and then also made sure that each one of the fibers is mated up and aligned in X, Y, Z. So it's still a 6 degree of freedom alignment, but in this case, it's really done by the pins engaging with the other ferrule.
Oh, okay. That's interesting.
And so what we have to do now is figure out how to do that same 6 degree of freedom, but now we have what we call expanded beam optics, which means that the light is propagating out of the fiber into the air or free space and then into the chip. And so now we have to align all 6 degrees of freedom via a machine in the absence of the pins.
Okay. That's interesting. Okay. I think I got it.
Also, the MPO connector is an example of a passive alignment. So you have structures developed on the connector, which guides the alignment process, right? So what we're doing is active alignment, which means there's no structures to guide it. There's just monitoring light, adjusting angles and positions, and then optimizing the signal going through the chip.
So just so I understand the difference between passive and active. When you say passive, it means that there's already how can I explain this? When there's already a structure that holds the alignment, and when you're talking about active alignment, is that there's some wiggle room or freedom to move until it reaches that stabilization.
Yep,
Am I correct?
And,
Yep.
Yeah.
And the machine is doing the wiggling,
Yeah.
Right.
not to some
I'm
structure.
understanding now.
The active element of it is the machine is doing the wiggling based on the signals between the devices. So the machine is live monitoring those signals, and as it sees the signals levels rising and falling, it uses that information to get the things into alignment. That's the active element.
Okay.
I kind of like to think of it as like a person walking up a hill. Right?
Okay.
So if you want to get to the peak, which is the best coupling efficiency of that light into the chip, you have to decide how you're going to get to that peak, right? And one of the ways you do is you look around and you say, which way is uphill and which way is downhill, right?
Mm-hmm.
You don't want to go downhill,
Yeah.
right? You go uphill. And so you're looking at the slope and the area around you to kind of guide you in what direction to go.
Okay.
That's what active alignment is doing. It's looking at how bright that light is, how strong it is, and trying to find the path that gives you that maximum and reach the peak of the light.
But what makes it even more difficult is that you don't know where the peak is.
Yeah.
And so as you're doing these, when you're monitoring light, you don't know if you're at the maximum yet, right? So you have to keep doing a little search here and there to find out if you've increased or decreased. And based off this feedback, you slowly find your way to the maximum.
It's kind of like somebody's
quickly.
telling you to find the
your
peak.
way to the maximum.
Hopefully rapidly find it. Yeah.
Ideally, yeah.
So
It's like
talking
somebody told you to find the peak, but then they blindfolded your eyes, and all you can see is the ground around your feet.
Yeah,
Right.
Yeah. Yeah.
So I think, Chris, because right now discussing the 6 degrees of freedom, I was going to ask you about what you just mentioned, just a little bit more detail, as how synchronized sensing with motion positions maps the power landscape to find a global optimum. How does that work?
I can take this one.
Okay.
What we're doing is the Santec power meters are integrated with our Aerotech motion controller, and so we're collecting real-time power level data across all of the channels that are being monitored, and that monitored data is being collected in real time. At the same time, we're collecting the position feedback data from our 6 degree of freedom positioner. And so what we're able to do is conduct a search in a 6 degree of freedom space. And as we conduct that search, we have all this data of the power levels. And so we're able to say, okay, when I was in this coordinate, I saw this power level. And then when I was in this next coordinate, I saw this other power level. And using that information, we can map basically a power map of the high dimensional search space. And by creating that map, that allows you to go up the hill. You can see the hills on the map once you have that information.
And does that process take long?
Used to.
Yeah, exactly. It
used
did
to.
until yesterday. So
Then it's a good thing that we had the podcast today.
Exactly. Our pickle line architecture is doing this process. It really depends on your acceptable threshold of dB loss, but ultimately we're seeing alignment times ranging from a second to under a second for certain processes, to single digit seconds for some other processes. So, and that's in comparison to some industry standards of tens of seconds and even minutes of an active alignment time. And so as Ryan mentioned earlier in the discussion, the active alignment step happens several times in the co-packaged optics supply chain. And one of the things that Senko is doing with their connector is trying to reduce the number of times you need to perform active alignment, but it can't be fully eliminated. And so even if we reduce the number of times, that active alignment process, if it's taking a minute per chip or something, you're talking about hundreds of thousands or millions of these devices on the scaling of data centers over the next few years. Really the only way to meet that demand is to break that bottleneck. And the pickle line architecture is how we're going to fix that problem in the industry.
Okay.
Yeah, it's kind of interesting to think about how many times you might do this, right? How many times might you do active alignment? So if you look at a typical first generation CPO system, right, it might have 32 optical engines in it.
Mm-hmm.
Each one of those is going to require a fiber optic connector. And in the production of that CPO module, each one of those engines may require 3, maybe 4 active alignment operations, right? So that means you're talking about at least 100 active alignment operations for every CPO module, right?
Wow.
Times industry demand of hundreds of thousands of units per month to 1 million units per month, right?
Wow.
It's a lot of active alignments. And so every second that you can take off of that alignment time, every tenth of a dB that you can recover in optical performance, it becomes really vital.
Okay.
And it's going to just get worse too.
Get worse, not better?
Well, fiber count increasing. So active alignment's going to get even more difficult if you don't use kind of a parallel alignment process that we're using. So,
Sorry to interrupt, but do you see this worsening soon, or maybe like in a couple of years? Because I know right now we're going up that hill, right?
Yeah.
But and do you see this if, let's say 5 years, we're good with this technology within 5 years, 10 years, or is it going to become sooner than that? When it actually gets worse?
I mean, Ryan probably knows a little bit more about future channel counts than I do, but I mean, we're working on 20 port devices now. There's going to be 40 soon. People are talking about 80, and channel counts are just going to keep going up. And the good thing about our system is it's expandable. So if you're working with the old method of only aligning one port at a time and then monitoring the other ports, you're just going to increase the amount of time that it's going to take for each of those alignments as channel counts go up. With ours, as channel counts go up, because it's all done in parallel, alignment time should stay fairly close to what it is.
Okay, so you just mentioned a very interesting thing that for whatever reason I was picturing in my mind, and I was like, okay, what happens to the architecture? So your system, you say that it's expandable, right?
Yeah.
Within that same space. Now I'm looking at from the outside. You're seeing inside the switch, and it's expandable. You're able to increase fiber counts. What does that do to the outside part where you have the actual cable and that management? Because if you say, 40, 80, let's say 120, whatever, it just keeps adding up. On the outside part, how would that look like? Because you still have the same capacity within the switch.
Yeah.
Then how does that look outside, or how would it look outside? That's what I'm trying to get at.
On the outside of the switch?
Yeah, because of cable management, right?
Yeah.
And space, airflow.
Yeah.
So routing
of the cables inside the CPO switches is going to be a real challenge, right? Because it's turning into spaghetti.
Hopefully not.
It's going to be organized spaghetti,
Okay.
right? But there's going to be a lot of fiber optic cables running around on these boards.
Me knowing what I know at the moment regarding cooling, energy efficiency, that's a problem because getting obviously not
Airflow.
The airflow, right? But getting those to a specific temperature, adding more cables to it, obviously decreases the airflow of that, and then just makes the room hotter, the racks hotter. So, are you seeing any type of different technology being applied to that part? I know we're getting a little bit off the subject of active alignment, but it was just a question that I just had.
I think most of the CPO systems are going to be liquid cooled.
Liquid cooled.
Yeah.
That's where we're heading at right now, right?
Absolutely.
Okay.
You're already there.
I think even at the front panels too, right? Like the ELSFPs, you
Yeah.
have a bunch of those connected to the front. They generate quite a bit of heat. Just laser sources running at like 23, 24 dBm of output power.
A layer higher, and kind of the problem there, though, is that's actually one of the reasons that CPO is being adopted. The energy efficiency, picojoules per bit of the data being transferred through CPO, current gen CPO devices, is several multiples more efficient than traditional transceiver methods. And so, given the scale of data centers and the growth being seen there, it's expected that CPO technology is going to save the industry billions of dollars a year in just energy consumption. So the heat's still a problem, but that energy it's a more efficient technology.
Okay, so Chris, why monitor all channels simultaneously? And what does greater than 40 dB single stage dynamic range buy you?
So, to monitor multiple channels in real time allows you, to optimize each of those ports in real time. So, if you're only measuring a single port, you kind of have no clue what's going on in the middle. So if you're typically what they do is they'd monitor a single port and then switch through the other ports. So it's a very time-consuming process. So if you're monitoring all ports in real time, you can see what's happening on all of those on those optical signals at the same time. And to be able to do that efficiently, you kind of need a wide dynamic range system. So our power meter, our current optical power meter is a linear amplifier, so it gives you greater than 40 dB of dynamic range, and that allows you to see from a dark signal, so where you don't have any light, to where you're fully lit. And what we're currently developing is a new power meter, which has, based off a log amplifier, which gives you 80 dB of dynamic range, so you can see even deeper into the dark level, and then can go 80 dB up to the very lit level.
Okay.
So if you take it back to thinking about the map and the terrain, what that sensing range, or that wide dynamic range, allows you to do is really to find the deepest valleys and the highest peaks.
Okay.
And know what that terrain is in between.
Yep.
Then Ryan, on the multi-channel sensing, what are the channel-to-channel sensitivity differences? And how is that driving alignment priorities?
Well, so each one of the CPO systems has, right now the main architecture is that the laser is separated from the co-packaged optics system. So that means you've got a laser that has a higher power, and that light has to be coupled into the CPO system. So you have those channels as input ports, and then you also have the communication channels as input and output ports. So one of the things that's clever about pick-align is it allows you to group those into separate monitors, right, through the optical power meters. And so that allows you to put priorities on different channels, right? So for instance, if you're losing a tenth of a dB on the high power laser coming in, that might be more important than losing a tenth of a dB on the IO channels. So you can prioritize those laser input channels to have even higher performance in the active alignment than in the IO channels.
Okay.
And as a system designer or a system modeler, that could be really beneficial to the energy efficiency of the entire system.
Justin.
Yeah.
Serial kinematics versus hexapod. What actually ships faster and repeats better in production?
So for the purposes of an active alignment application, a serial kinematic architecture is the better option because the positioning accuracy and repeatability is going to be tighter than a hexapod. And what I mean by that is if you go to a given 6 degree of freedom position with your serial kinematic architecture and then go to another position and then try to go back to your first position, that system will perform that step with better accuracy, better performance by a significant margin than what you would see with a hexapod. A hexapod or a parallel kinematic architecture. Really, that's because there's fewer moving components, there's fewer sources of error in that move than what would be introduced by a hexapod. Additionally, serial kinematic architecture allows you to conduct more dynamic motion, faster accelerations, faster speeds, and those accelerations play into the speed at which you can conduct your alignment search. And so a hexapod ultimately could do the same moves that the serial kinematic stack can do. It just can't do them as precisely and it can't do them as fast. That being said, there are applications where hexapods or other parallel kinematic architectures are the right solution. But for this specific application, we see meaningfully better for performance with serial kinematics.
I had a question for you, Justin. Actually, I had a customer yesterday talking to me about they have an alignment system.
Yep.
And I'm not sure what type of, if they were using a hexapod or serial. They mentioned that when the machine moved to its final spot, there was still a PID that was working, and then the system was still moving.
Yep.
Is that different between serial versus hexapod?
So you would see that in both types of architectures. I don't know the exact data, but I do know that we have specific amplifier designs, including a newly launched PWM Plus is what it's called. We recently launched in the last few months, where basically it's optimized to reduce noise. And so in a serial kinematic system, we can get those noise levels down to like a nanometer, or a few nanometers. That being said, with a hexapod, some of the compliance in the physical architecture of a hexapod can help dampen out that noise. Okay. So I actually might expect that oscillation to be potentially smaller on a hexapod because the motors are not directly coupled to the actual work point. But that being said, these types of applications, active alignment, are not traditionally sensitive to a single nanometer. So since we're orders of magnitude smaller than the sensitivity of the devices, that doesn't tend to play a role, at least for our systems. Yeah. That being said, there's other systems on the market that have much higher noise bands in their resting position, and it sounds like maybe that's what they were seeing.
Okay, all right. Sorry for hijacking it.
No. That's a really good question. I loved that part. So Ryan, what are the process steps that benefit repeatability?
Okay. So the repeatability is really important in the active alignment. You can think about it in kind of two ways. One of them is to think about when you're doing testing, right? So for instance, if a company wants to test the electro-optical performance of the PIC, then they need to move the fiber connector over those I/O ports, find the optimum position, and then they may run a battery of tests. And then they may need to move the connector, do something else, come back the next day, move that connector back to the exact same alignment position and repeat those tests. So there's repeatability in the sense that, you do the alignment and then you swap a connector or you swap out a chip and you want to go back to that exact same alignment position. There's that kind of repeatability. Then the second one is, we do when you're attaching a device to the chip, you often use some sort of glue to attach it, and so that's often a two-step active alignment, meaning that you first find the optimum position, and then you remove the connector, dispense the epoxy, and then you want to go back to that exact perfect alignment position, and so you have a second opportunity where repeatability is important.
Oh, okay.
During the epoxy process, I think there's also a need to monitor optical performance during that process, right? So
Absolutely.
so this system also allows the customer to monitor in real time during that epoxy process. And I think there's even a lot of times during the epoxy, the FAU might shift a little bit. And so I believe the Aerotech team is also working at, while the epoxy is hardening, also doing fine alignments to keep the insertion loss low during the epoxy process. And they can do that on all ports instead of just monitoring one port.
Okay. So what instrumentation artifacts are you to avoid when motion gets fast, like gain staging or the source drift?
Yes. So with your power meter needs to be as fast as the alignment process. So if the faster you need to move the motors or the positioners, your power meter also needs to have a wide bandwidth to be able to accommodate that, and also needs to be able to go from a very low signal to a high signal quickly. So you need a wide bandwidth for that. On the optical source, you really just need that to be stable. It needs to be nice and quiet so that as the motion system is reading the voltage levels from it, those voltage levels aren't changing quickly based off noise. You want that change to be based off the actual true optical signal.
Got it. Okay.
Kind of comes down to like back to the map analogy. As you're drawing your map, if the sources aren't stable and the detectors aren't stable, you're going to get bumps in your map that are not actually from the topography. They're from the optical instrumentation. So the stability of those devices is critical for drawing that map.
And that really is necessary to achieve repeatability too, right? So if the laser source is drifting over time, or the sensitivity of the power meters is drifting over time, then you won't be able to achieve repeatability.
Yeah.
So
okay.
I think that's one of the real values in this collaboration, right? It brings together the stability from the Santec instrumentation along with the stability in the motion control system. And without both of those, it's really hard to achieve repeatability and high speed.
Yeah.
From repeatability to now manufacturing at scale. So with Ryan, like how detachable FAUs and early bonded receptacles remove dangling fiber headaches and enable late stage attachments?
The trend right now in CPOs is to be able to have a fiber optic connector that's detachable, right? So that means that you can mate the fiber optic connector to the chip and then demate it, remate it, demate it, remate it, demate it multiple times. One of the ways of doing that is to put a device called a receptacle onto the chip. And then every mate or demate cycle after the attachment of that receptacle is completely passive. You don't need to do the active alignment. So that allows us to push the active alignment to be exclusively at the earlier part of the supply chain, when you're testing the chips, when you're testing the dies, when you're attaching the receptacle. So those are kind of three now key points in the supply chain where active alignment is needed.
Okay.
Another aspect of that as well is to use a very different analogy, but if you think of the chip where the fiber optic connections are happening, Senko's connector allows you to detach those fiber optics. And so the analogy would be like if you needed to move a PC from one room to another, you would detach all the cables, and then you can just move that more easily, and then you can reattach everything on the other side. If you use a permanent attach method of your fiber optics, it would be like moving your PC from one room to another, but you have to keep everything plugged in the whole time, which is a much bigger hassle for production. So,
especially when you think about 1,000 optical fibers dangling off.
Yeah, multiply that problem by 200, and you have an idea of how challenging that could be. And so that detachability becomes really important in manufacturing and test.
Okay. Oh, wow. Okay.
So it allows the semiconductor industry to really build these CPO modules without fibers dangling off the sides. Yeah. And then you can simply mate those connectors when you're building the final box.
And also serviceability in the field too. So if there is an issue with optical connectivity to the chip, you can just replace the cable instead of having to take the whole the whole chip out.
I want to do like a really quick, fun lightning round. Just one simple question. Well, one to each. So Ryan, myth or fact? Detachable expanded beam interfaces can't meet production grade repeatability. I said it.
That's a myth.
That's a myth.
Yeah. They
We're-
can meet it.
They can meet it. We're meeting that right now.
We're meeting that right now.
Yes. Okay. Cool. Justin, finish the sentence. The hidden killer in 6 degrees of freedom alignment is?
A low performance motion system that can't consistently find the same optimum and consistently return to your optimum alignment position.
Okay. Chris, a quick hit. One thing teams underestimate about multi-channel sensing is?
The difficulty of it, I would say. They think it's easier than it is, maybe.
That was kind of my thing as well. Like when we started this pick and then going to a scale manufacturing at scale, I would always see like the supply chain team members from at Senko that they were struggling. Like why? Like how? And I used to work in supply chain, and I always thought like, if they put me in that project, I'll solve it in like 2 months. And that was obviously my ego, but
We should have brought you in. This path would have been a lot easier.
But I've always wondered, why is this so difficult? And now that I know, I mean, obviously reading more and talking to all of you, I know that it's a very difficult thing to achieve because it's not as simple as people think. But for regular folks that are not like very invested, that's how we see it. We see it as like, that shouldn't be so hard. We're dealing with microns and like very small units. Why is this so hard having all this technology at our fingertips? So that was, I just wanted to make that statement. It's not a question, but it's one of the things that people externally, we perceive as that way, but we are never fully into like how we know how difficult it is.
Yeah, I think one of the things that the CPO has done is kind of really tested the entire ecosystem and the entire supply chain.
Yeah.
It's kind of pushing every step in that supply chain to do something they've never done before.
Yeah.
And
Okay.
that's different materials, it's different components, it's different cables,
Okay.
Processes.
different processes, different reliability requirements. And so it's really an evolution in the entire industry.
Okay, so that's where I was going to get at. This basically isn't a game changer, industry changer, right? So we're reshaping the industry from this point on.
That's correct.
Okay. Yeah, we're part of history.
Yep.
Hopefully so.
I appreciate the time. I appreciate all of you guys being here and your willingness to do this. This was very fun and the first for all of us.
Yeah, it
So,
was fun.
Thank you.
It was fun.
Appreciate it.
Yeah.
Yeah.
No, thank you for being here.
Thank you,
So-
Arturo.
This
Thank
is
you guys.
probably the most aligned podcast you'll ever have.
No,
Cool.
Thank you guys.
Thanks.